In this video, I will show you how to integrate using partial fractions. This is a BC only topic. Let's start with some algebra. How do we add two rational expressions and combine them to form one rational expression? We start by forming like denominators. The second denominator is x squared plus 1. So, to have like denominators, the first denominator will also need an x squared plus 1 factor. We can add this as long as we do the same thing in the numerator and the denominator. This way we are really multiplying by 1, so we're not really changing the value of the expression. On the right hand side, we notice that the first denominator has an x. So that means the second denominator will also need an x, so we multiply by x over x. Now we have like denominators, so we can combine these two rational expressions into one. We will certainly keep the common denominator of x times x squared plus 1. But let's go ahead and do the distributive property so we can get rid of the parentheses. So in the numerator we have 5x squared plus 5 from the first fraction, and distributing this x we have plus 3x squared plus 2x. Let's combine like terms. 5x squared plus 3x squared is 8x squared. And then we have the plus 2x and plus 5. And that's how we combine two rational expressions into one. We get partial fractions when we go in reverse. We want to take this single rational expression and rewrite it as the sum of two rational expressions. We are going to use the two factors as separate denominators. So we want an x and then an x plus 2. But what goes in the numerator? I will tell you what doesn't go in the numerator. It's definitely not going to just be x and then minus 6. If we made like denominators and put this together, it would not give you the original function. So how do we figure out what the actual numerators should be? For right now, let's just use a and b as placeholders. To solve for a and b, we need to start by multiplying both sides of this equation by the common denominator x times x plus 2. Notice that on the left side, the x times x plus 2 and this x times x plus 2 cancel each other out. On the next fraction, the x's cancel out, and on the final fraction, the x plus 2 and the x plus 2 cancel each other out. Let's look at what's left. On the left, we just have x minus 6. For the next term, the x's cancel out, and we are left with a times x plus 2. And then for this last term, the x plus 2's cancel out, and we are left with bx. After this, there are two ways to solve for a and b. For the first method, we bring down the x minus 6, and we distribute the a. So we have ax plus 2a. And then bring down your plus bx. So next we have x minus 6. And I'm going to put these like terms together. So I have ax plus bx plus 2a. Normally I wouldn't show this step, I would just sort of do this in my head. But then on the next line we will have x minus 6 equals, and I'm just going to take out the x. I'm going to factor out the x, and that's going to leave behind a plus b times x plus 2a. Next, we can make a little system of equations by setting the coefficients equal to each other. The coefficient of x on the left is 1, and the coefficient of x on the right is a plus b. That means 1 must equal a plus b. Also, on the left, the constant coefficient is negative 6, and on the right, the constant coefficient is 2a. That means negative 6 must equal 2a. Notice that we can solve this second equation by dividing both sides by 2. In other words, a is equal to -3. Let's substitute that in for a right now. Now we have 1 is equal to -3 plus b. Adding 3 to both sides, we get b is equal to 4. So we just found a and b. Let's plug both of these values back into this expression right here. We get -3 over x plus 4 over x plus 2. This is called the partial fraction decomposition of x minus 6 over x times x plus 2, and these expressions are equivalent. Method 2 is to find a and b by plugging in values for x. You can plug in whatever values you want into an equation. However, it will be most helpful if you pick a value that will make these terms disappear one at a time. For example, this term will disappear if x is equal to 0. So let's plug in 0 for all of the x's. On the left side of the equation, that will leave us with -6. And then on the right-hand side, the second term is gone, but we still have a times 0 plus 2. In other words, 2a. Now we can solve for a by dividing both sides by 2. So we get a is equal to -3. Notice that's the exact same thing that we got by using method 1. The first term will disappear if I let x equal -2. So let's let x equal -2. On the left side, we have -2 minus 6. So that's -8 equals. And then -2 plus 2 is 0. 0 times a is 0. So that's why this term is gone. But we are still left with b times -2. In other words, -2b. We can solve for b by dividing both sides by -2. That gives us b is equal to +4. These are the same values that we got by using method 1, so of course when you plug them back in, you get the same answer. Method 2 is usually easier when both factors in the denominator are linear. Notice we don't have any x squared anywhere. When the factors of the denominator are quadratic, then sometimes method 2 doesn't work and we have to do method 1. But most of the time we are going to be using method 2. Now let's try one with 3 factors in the denominator. Our partial fraction decomposition will have a term for each factor from the denominator. Next, we want to multiply both sides of the equation by the common denominator. A lot of things will cancel out. Let's see what survives. On the left side, the entire denominator is canceled out by the common denominator. So only the numerator is left. Next, let's take the common denominator and multiply it by the term a over x plus 1. In this case, the x plus 1's will cancel each other out. So we are left with a times x minus 1 times x minus 2. When we multiply the common denominator times the middle term, the x minus 1's cancel each other out. That's going to leave us with b times x plus 1 times x minus 2. When we multiply the common denominator by the final term, the x minus 2's cancel each other out. That will leave us with c times x plus 1 times x minus 1. Let's try to do this problem by method 1, but it's not going to be pretty. Multiplying x minus 1 times x minus 2 gives us this. X plus 1 times x minus 2 gives us this, and x plus 1 times x minus 1 gives us this. If you distribute the a across the trinomial, you get this expression. Similarly, if you distribute the b, you get this. And if you distribute the c, you get this. Let's group the like terms together. So first we have ax squared plus bx squared plus cx squared. However, let's factor out the x squared. So now we have this. If we group the linear terms, next we have negative 3ax minus bx. If we factor out the x, we get this. Finally, let's group together the constant terms. So that's plus 2a minus 2b minus c. Next, we can set up a system of equations by setting the corresponding coefficients equal to each other. Starting with the red quadratic terms, we have a plus b plus c is equal to 2. Setting the coefficients of the linear terms equal to each other gives us negative 3a minus b is equal to negative 13. Finally, setting the constant terms equal to each other, we get 2a minus 2b minus c is equal to 3. We can solve this system of 3 equations and 3 unknowns using substitution and elimination. Let's start with the middle equation because it only has 2 variables. Adding b to both sides and adding 13 to both sides gives us b equals negative 3a plus 13. Let's substitute this expression in for b right here. Then we have a minus 3a plus 13 plus c is equal to 2. Simplifying like terms right here gives us negative 2a plus 13 plus c is equal to 2. Subtracting 13 from both sides, we get negative 2a plus c is equal to negative 11. That's as far as we can go with that for now. But let's take this expression for b and substitute it in the equation on the right. So now we have this. Distributing the negative 2 gives us this. If we combine 2a plus 6a, that is 8a. And if we add 26 to both sides, we have 8a minus c is equal to 29. Notice that the red equation and the green equation are both written in terms of a and c. We can combine these and solve them using elimination. So I'm just going to bring this over here and line it up. So we have 8a minus c is equal to 29. Combining like terms gives us 6a is equal to 18. Dividing both sides by 6, and we get a is equal to 3. 1 down, 2 to go. We can find b by substituting 3 in for a right here. b equals negative 3 times 3 plus 13, so b is equal to 4. We can also find c by substituting 3 in for a right here. So we get 8 times 3 minus c is equal to 29. In other words, 24 minus c is equal to 29. Adding c to both sides and subtracting 29 gives us c is equal to negative 5. Remember that a, b, and c are the numerators of these 3 rational expressions. So let's substitute the 3 values that we just found back in for the final answer. So that's how you find the partial fraction decomposition using method 1. But this is going to turn out to be the long way. Let's go back and do the same problem using method 2, which is sometimes called the Heaviside method. Let's pick up from the step where we have just multiplied both sides of the equation by the common denominator, so all of the denominators have been canceled out, and we have this. For method 2, we want to find a, b, and c by plugging in certain values of x on both sides of the equation. We want to choose values of x that will cancel out as many terms as possible. For example, if we pick x equals -1, that will cancel out every term that has a factor of x plus 1 in it. So this term is going to be gone because -1 plus 1 is 0, and this term is going to be gone because the x plus 1 will become 0 when you plug in -1. That's going to leave us with, on the left side, -1 squared is +1. 2 times +1 is 2. So I have 2, and then -13 times -1 is +13, and then we have the +3. So that's what we get on the left-hand side if we plug in -1. As I mentioned, these terms are gone, so we are left with a times -1 minus 1 is -2. So we have a times -2, and then -1 minus 2 is -3. Adding these terms together, that's 16, 18. On the right-hand side, this is 6a. So we have 6a is equal to 18. Dividing both sides by 6 gives us a equals 3. 1 down, 2 to go. That was a lot faster so far. Next, let's let x equal +1 to make the factor of x minus 1 equal 0. On the left-hand side, this will be 2, and then -13, because -13 times 1, and +3. This will equal, so remember, any term that has x minus 1 in it will go to 0. So I see the x minus 1 right here, so that's going to be 0. And I see the x minus 1 here, so this is going to go to 0. That's going to leave b times 1 plus 1 is 2, and 1 minus 2 is -1. -1 times 2 is -2, so we have -2b equals -8. Dividing both sides by -2 gives us b equals 4. Alright, 2 down, 1 to go. If we let x equal 2, that's going to cause the factor of x minus 2 to equal 0. So these two terms will end up being canceled out. So let's let x equal +2. On the left-hand side of the equation, we have 2 squared, which is 4, times 2, which is 8. And then we have -13 times 2, which is -26, plus 3. And then on the right-hand side, these two terms are gone. If x is equal to 2, then we have c times 2 plus 1, which is 3, and 2 minus 1, which is just 1, which I'm not even going to write down. So we now have 3c equals -15. Dividing both sides by 3 gives us c equals -5. These are the same three values we got from method 1, so of course we get the same partial fraction decomposition. You'll probably agree that method 2 was the faster method this time. This will usually be the case when all of the factors are linear, x minus 1, x minus 2. In a future video, we will run into problems where we have quadratic factors like x squared plus 3. When we have quadratic factors, it is very difficult to pick values of x that will cancel out multiple terms. So we will have to use method 1. So far we've been doing a whole bunch of algebra. How will partial fractions help us integrate a problem like this one? First of all, notice that we cannot use substitution like we normally do when we notice that the degree of the numerator is 1 less than the degree of the denominator. For example, if we let u equal 4x squared minus 9, then u prime is going to equal 8x. But 8x does not cancel out the 8x that's in the numerator because of the pesky plus 18. You can't cancel out something that's connected by addition. So it's partial fractions to the rescue. But the first step is to factor the denominator. Don't worry about the numerator. Now we need to find the a and b that will allow us to rewrite the integrand as a over the first factor plus b over the second factor. Let's multiply both sides of the equation by the common denominator. On the left, if we multiply by the common denominator, the denominator cancels out and we just have 8x plus 18. If I multiply this term by 2x plus 3 times 2x minus 3, the 2x plus 3 and this 2x plus 3 cancel each other out. But that leaves a times 2x minus 3. Similarly, if I multiply the last term times 2x plus 3 times 2x minus 3, the 2x minus 3 cancels out the 2x minus 3. But that leaves plus b times 2x plus 3. Now let's plug in values of x that will cancel out one term at a time. If we set 2x plus 3 equal to 0 and solve, we get negative 3 over 2. So let's start by letting x equal negative 3 over 2. Remember, that will cause this factor to equal 0. So that means this time around, this factor is going to disappear. On the left-hand side, we have 8 times negative 3 over 2 plus 18. And this will equal a times 2 times negative 3 over 2 minus 3. Negative 3 times 8 is negative 24. Divided by 2 is negative 12. So we have negative 12 plus 18 is equal to a times. The 2's cancel each other out, and we just have negative 3 minus 3, which is negative 6. In other words, we have negative 6a is equal to 6. Dividing both sides by negative 6 gives us a equals negative 1. To find b, we would love to cancel out the a term. If we set 2x minus 3 equal to 0 and solve, we get 3 over 2. So let's let x equal 3 over 2. This time around, the a term will go to 0, so that's gone. Substituting 3 over 2 in for x, we have 8 times 3 over 2 plus 18 is equal to b times 2 times 3 over 2 plus 3. 8 times 3 is 24, divided by 2 is 12. So we have 12 plus 18 equals b times. The 2's cancel out, and we have 3 plus 3, which is 6. In other words, we have 6b is equal to 30. Dividing both sides by 6 gives us b is equal to 5. Rewriting the integral using our partial fraction decomposition gives us this. Let's integrate term by term using mental U substitution. The -1 in the numerator becomes a negative sign out in the front. Let's imagine that the denominator is u. Therefore, u prime is 2. So we wind up dividing by u prime. So we will have a 1/2 in the front. So we have the integral of 1 over u. That's going to be the natural log of the absolute value of u. In other words, the natural log of the absolute value of 2x plus 3. Similarly, the 5 in the numerator is going to come out in the front. And using our mental u substitution, u prime again is 2. So we need to divide by 2. So in fact, instead of just putting 5, let's write 5 halves. So we have 5 halves times the natural log of the absolute value of 2x minus 3, and don't forget your plus c. So that's how you use partial fractions to allow us to integrate something that we could not integrate using u substitution. So how do we know when we need to use partial fractions to integrate? There are 3 things to look for. Number 1, regular u sub doesn't work. Number 2, the degree of the denominator must be greater than the degree of the numerator. And number 3, the denominator must be factorable. If these 3 conditions are met, that's when we will use partial fractions. Will we use partial fractions to help us integrate this example? First of all, the degree of the denominator is greater than the numerator, so maybe. Will normal u substitution work? If we let the denominator equal u, then u prime is going to equal 4x plus 7. This will not cancel out the x in the numerator, so normal u substitution will not work. We will use partial fractions as long as the denominator is factorable. 2x squared will factor as 2x times x. 3 will factor as 1 times 3. Outer we have 6x, and inner we have 1x. That makes a middle of 7x, as long as we leave the signs as both positive. So the denominator is factorable. Let's do partial fractions. We need to rewrite this integrand as a over the first factor plus b over the second factor. Let's multiply both sides of the equation by the common denominator. If we multiply the left side by 2x plus 1 times x plus 3, the denominator cancels out, and we are left with x plus 8. If we multiply this term by the common denominator, the 2x plus 1 and the 2x plus 1 will cancel each other out. That will leave a times the x plus 3. If we multiply this common denominator times the last term, the x plus 3 and the x plus 3 will cancel out, and that will leave behind b times 2x plus 1. If we set 2x plus 1 equal to 0, we get negative 1/2. So if we let x equal negative 1/2, 2x plus 1 will go to 0, and this term goes away. Substituting negative 1/2 in for x here and here gives us this. 8 is the same as 16 over 2, and 3 is the same as 6 over 2. So we get 15 over 2 is equal to 5 over 2a. Multiplying both sides by 2 gives us 15 equals 5a. Dividing both sides by 5, and we get a is equal to 3. Next, let's let x equal negative 3, so this term will be canceled out and taken to 0. Plugging in negative 3 for x right here, we have negative 3 plus 8, which is 5. So we have 5 is equal to b times 2 times negative 3 is negative 6, plus 1 is negative 5. dividing both sides by -5 gives us b equals -1. Rewriting the integral using our partial fraction decomposition gives us this. Now we can easily integrate term by term. We have this 3 in the numerator. That's going to come out in the front, and we will do a mental u substitution. If we let u equal 2x plus 1, u prime is 2. We end up dividing by u prime, so we have to divide by 2. That leaves us with the integral of 1 over u, which is the natural log of the absolute value of u. In other words, the natural log of the absolute value of 2x plus 1. The negative sign is going to come out in the front, and we have the integral of 1 over u, which is the natural log of the absolute value of u, plus c. So that's it for example G. Will we need partial fractions for example C? Well, the degree of the denominator is greater than the degree of the numerator, so maybe. Will regular u substitution work? Let's try. If we let u equal the whole denominator, so let's let u equal x to the third power plus 6x squared. In that case, u prime will equal 3x squared plus 12x. Will this somehow cancel out the numerator? In the numerator, I don't have any number in front. It's just x squared. So let's see what happens if we factor out a 3. U prime will then be 3 times x squared plus 4x. Wait a minute, x squared plus 4x. That will cancel out the numerator. So we will not need partial fractions. We can just do regular u substitution. If we do this substitution, we have x squared plus 4x in the numerator. The denominator is u. And we replace dx with du over u prime. In other words, du over 3 times x squared plus 4x. The x squared plus 4x cancels out the x squared plus 4x. The 3 comes out in the front as a 1/3. So I have 1/3 times the integral of 1 over u du. So we have 1/3 times the natural log of the absolute value of u. In other words, the absolute value of x to the third power plus 6x squared plus c. So we could have used partial fractions to solve this, but that would have been the long way. When you see trig functions being added or subtracted in the integrand, you can often solve the problem by first doing u substitution and then partial fractions. So let's let u equal sine x, which means that u prime will equal cosine x. Performing the substitution, we have cosine x over u minus u squared. Instead of dx, we write du over u prime. In other words, du over cosine x. So cosine x cancels out, and we are left with the integral of 1 over u minus u squared du. Time for partial fractions. Let's start by factoring the denominator. So we have the integral of 1 over u times 1 minus u du. We need to rewrite this integrand in the form a over u plus b over 1 minus u. Multiplying both sides of the equation by the common denominator, on the left side the common denominator cancels out and we just have 1. On the next term, if we multiply by this common denominator, the u and the u will cancel out and that leaves a times 1 minus u. When we multiply the common denominator by the second term, the 1 minus u cancels out the 1 minus u, and that leaves b times u. If we let u equal 0, that cancels out the second term. So we are left with 1 is equal to, well, 1 minus 0 is just 1, so it's really a equals 1. If we let u equal 1, we have 1 minus 1, so that's 0, which cancels out this term. That leaves us with 1 equals b times 1, of course, is just b. Now the integral becomes the integral of 1 over u plus 1 over 1 minus u du. Integrating term by term, we have the natural log of the absolute value of u. Be careful on this second one. We have to do another substitution here. The derivative of the denominator is negative 1. So we will end up with a negative out in the front. But then we just have the natural log of the absolute value of the denominator, 1 minus u, plus c. Before we get the x's back in here, let's use the properties of logarithms to simplify this part a little bit. Remember, natural log p minus natural log q is equal to natural log of p over q. So we can simplify this by writing the natural log of the absolute value of u over 1 minus u. Now let's substitute sine x back in for u. So the final answer is the natural log of the absolute value of sine x over 1 minus sine x plus c. This last problem has one extra step. We can't use partial fractions right away because the degree of the numerator is greater than the degree of the denominator. But that just means we need to do long division first. You set up your long division like this. X to the third power divided by x squared is x. So that's what goes up on the top, and I like to line up those like terms. Then you take the x and you multiply by the divisor. So x times x squared is x to the third power. X times 2x is 2x squared. And then you subtract. X to the third power minus x to the third power is 0. 5x squared minus 2x squared is 3x squared. There's nothing to subtract from the 6x and the 4, so you just bring those down. And then you start over. 3x squared divided by x squared is 3. So that's what goes on the top. Then you multiply. 3 times x squared is 3x squared. And 3 times 2x is 6x. And that's it. Then you subtract. That cancels out both of these terms, and the 4 just comes down. So the 4 is the remainder. And the way you handle the remainder is you put a plus, and then you put the remainder over the divisor. So we have rewritten this integral as the integral of x plus 3 plus 4 over x squared plus 2x dx. This integral is equivalent to the original integral. Looking ahead, I can see that we will not be able to integrate this purple term the way it is. We need to do partial fraction decomposition. So let's get ready by rewriting this as 4 over x times x plus 2. And then we need to rewrite this as a over x plus b over x plus 2. Multiplying both sides of this equation by the common denominator, on the left side, the denominator cancels out and you're left with 4. When you multiply the common denominator times the middle term, the x and the x cancel out, and it leaves you with a times the x plus 2. When you multiply this common denominator by the last term, the x plus 2's cancel out, and you are left with b times x. If we let x equal 0, it cancels out the second term. So we are left with 4 equals, and then if x is 0, then we really just have 2a. Dividing both sides by 2 gives us a is equal to 2. If we let x equal negative 2, it cancels out the first term. So we are left with 4 is equal to b times negative 2. In other words, negative 2b. Dividing both sides by negative 2 gives us b equals negative 2. Next, we rewrite this integral using our partial fraction decomposition. So we still have the integral of x plus 3, which is right here. But instead of this purple term, we are going to write the a over x plus b over x plus 2. In other words, 2 over x plus negative 2 over x plus 2. So our new integral is this. Let's integrate term by term. The antiderivative of x is 1/2 x squared. The antiderivative of 3 is 3x. And this 2 is going to come out to the front, so we really are integrating 1 over x, which is the natural log of the absolute value of x. This negative 2 is going to come out in the front, so we really have the integral of 1 over x plus 2, which is going to be the natural log of the absolute value of x plus 2. Technically, I did a mental u substitution right there, but if u is x plus 2, then u prime is just 1. Dividing by 1 changes nothing, so there you go. All we need to finish off the answer is our plus c. So that's our introduction to integration using partial fractions.